Let's continue with our lecture on the analysis of singly reinforced rectangular beam section. So before going into our slide, let us look at this Annex G of our IS code 456. In our previous lecture also we referred to this Annex G and said that some formulas were given in this annex and we derived those formulas. So this annex, which is related to clause 38.1 of our code, gives us the moment of resistance for rectangular and T sections. So in section G 1.1, it gives us formula for sections without compression reinforcement. This means these are the singly reinforced rectangular beams. What it says is the moment of resistance of rectangular sections without compression reinforcement should be obtained as follows. First, we have to determine the depth of neutral axis. We derived this formula xu by d in our previous lecture also. We equated tensile force with compressive force, and we put this value of FSC, which is the stress in tension steel, as 0.87 Fy, and then we divided both sides of this equation by d, and we got this formula here. Now, if the value of xu by d is less than the limiting value, we derived limiting values also in our previous lecture. This limiting values was based on the value of Fy. We use the similar triangle property. We use similar triangle property in our strain diagram, and then we derive the value of limiting value of xu by d. So if the value of xu by d is less than that limiting value, we use this formula to calculate the moment of resistance. If the value of xu by d is equal to the limiting value, we use this formula to calculate the moment of resistance. But if the value of xu by d is greater than the limiting value, then the section will be redesigned, since now our beam will be over reinforced. So we will look at these two formulas today, and in our next lecture, next two lectures I think, we will probably see numerical relating to the analysis of singly reinforced rectangular reinforced concrete beam. So let me close this and let me go to my presentation. So resisting moment strength for balanced sections. We know the formula for the nominal or theoretical moment resistance given by T into Z. T is the tensile force and Z is the lever arm. We also know the value of xu. Now we combine these two equations by substituting the value of xu here. Then we will get this formula. If you simplify it by multiplying these constants, then the multiplication of this constant will be nearly equal to 0.36, so that this 0.36 and 0.36 will cancel, and then we will take d common from here. We will get the value of mn as 0.87 Fy ast d 1 minus this value here. So this is the formula that is given in Annex G. This was given in G 1.1 in number B. So this formula is to be used when the value of xu by d is less than the limiting value, as we saw in our Annex G also. So what we want to do here is we want to replace this AST, which gives us the value of steel reinforcement in terms of percentage. So let the area of tensile steel be denoted as a percentage of the effective beam area, so that PT, which means the percentage of tensile reinforcement, is AST over BD. B is the width, D is the effective depth. So this becomes the effective beam area into 100. And if you substitute the value of PT in this equation phi here, then you get the value as mn by BD square is 0.87 Fy PT over 100 and 1 minus Fy over FCK PT over 100. So again, this is for PT less than the limiting value of tensile reinforcement percentage. I have written this formula in the next slide also. Let's see here. So now we got an equation not on the terms of AST but on this terms of PT here. So by using this above equation, different tables have been derived. And these tables you can find in this SP16. SP16 is a special publication. SP means the special publication of ISI, Indian Standard Institute. And this SP16 acts as a design aid for reinforced concrete to IS 456 1978. In this book or in this manual, you can find various tables and various charts that are helpful in the design of reinforced concrete structure. And in this course of reinforced concrete design, we will refer to SP16 as those topics come along. So if you look at SP16 1980, there are 4 tables, table 1 to 4, which gives us the value of this Mn over Bd square. Or in SP16, it is represented as Mu over Bd square, the percentage of steel for different values of Fy and Fck. So using this formula here, different tables have been generated. For given value of Fy, Fck, Mu over Bd square, the percentage of steel has been calculated. I have included one such table for reference here. If you see table 1, which is the reinforcement percentage for singly reinforced section, it gives you the value of percentage of steel reinforcement for concrete grade 15 Newton per mm square. In table 2, it is given for 20, in table 3 for 25, in table 4 for 30. So I have only presented here table 1. If you see here, the value of Mu by Bd square in Newton per millimeter square, Newton per millimeter here. Check this unit once yourself. And for different grades of Fy, 240, 250, 415, 480, 500. Similarly, 240, 215, 415, 480, 500. So for given values of Mu over Bd square, Fy and Fck, this table presents the value of Pt, that is the percentage of steel reinforcement. So if you want to use SP16 in your design process, you need not use this formula. Instead, you can directly refer to these tables here. So this is one easier way to analyze your structure. Instead of using these big formulas, you can directly use the tabulated values given in SP16. So now you can see that this equation here, this equation is quadratic in the term Pt by 100. So how do we get the value of Pt? You can solve this quadratic equation for Pt, then you will get the value of limiting value of Pt, which is given by this formula here. This Pt limiting is the limiting percentage of tensile steel corresponding to the limiting moment of resistance, Mu, or Mu limiting. So in this way, we have one formula for Pt limiting here. And finally, in our Annex G 1.1, there was another formula in C where that formula was to be used when the value of X by D is equal to the limiting value. So this formula has also been derived using the same equation. Previously, when we wanted to derive the formula for X by D less than the limiting value, we used the moment strength based on the steel tensile strength. Now we will use our nominal moment strength based on the compressive strength of our concrete, C into Z. C means this and Z is here. So to express this equation in terms of X by D, what we will do is we will divide both sides of this equation by Bd square. So Mn limiting by Bd square means now you will get 0.36 Fck, Xu limiting by D, and 1 minus 0.416 Xu limiting by D. So once we substitute the value of Xu limiting by D or Xu by D limiting value, which we derived in our previous lecture, we will get the value of this Mn limiting by Bd square. Similarly, by substituting the value of this Mn limiting by Bd square, we can get the value of Pt limiting. So you can see in our previous lecture here, If to substitute the value of mn by bd square, limiting values of mn by bd square, then we can get the limiting value of pn also. So if you do all these things, you will get one table here. This table is frequently used in our numerical process, so just remember. You do not need to memorize the values. We will refer to this table time and again. For Fy of different grades here, the limiting value of mu limiting by fck bd square has been given, and similarly pt limiting Fy over fck has been given. So if you want to find the maximum or limiting value of mu limiting, moment of resistance, then you can use these formulas here. For 250 grade steel, it is 0.149. If you take this fck bd square to the next side of the equation, it will be fck bd square. Similarly, for 415 grade steel, it will be 0.13k fck bd square, and for 500 grade steel, it will be 0.133 fck bd square. So this is for 250, this is for 415, and this is for 500. Similarly, if you want to find the limiting percentage of tensile reinforcement, let me write it with a different color here. This value of PT limiting for 250 grade steel will now be 21.97. If you take this to the next side of the equation, you will get fck over fy. Similarly, for 415 grade steel, 19.82 fck over fy, and for 500 grade steel, 18.87 fck over fy. So if you are given a rectangular section to analyze, and you are given certain value of AST, you can convert that AST into the percentage by dividing it by BD into 100. You can find the limiting value of the percentage of tensile steel reinforcement based on these formulas for your particular grade of steel that is used, and then you can compare this actual value of PT used to the actual value of PT limiting. And if the actual value of PT used is less than PT limiting, yours is a under reinforced section. If these are equal, it is a balanced section, and if higher amount of reinforcement has been used, it is your over reinforced section. So these formulas can be very useful in doing the numerical for analysis of your sections. So the final conclusion of all of these formulas. So we have derived different formulas from different viewpoints, and these need not be used all at once in a single numerical or in a single analysis. We will use these formulas based upon our need. But what you have to remember is the moment capacity of a singly reinforced section is restricted to Mn limiting, which is given by this here. So for example, if you are given a certain value of ultimate moment that is acting or coming onto your section, and you can calculate the value of limiting moment of your section based on this grade of steel used. If the limiting value of your section is less than the actual value of moment that is coming onto your section, then you will have to redesign the section. But if this acting moment mu is less than the limiting value, then that beam section can be designed as under reinforced. So Mn limiting is the restricted value up to which your singly reinforced section can resist the ultimate moment. So even if the beam has more reinforcement than that required for a balanced section, the increase in strength will be very minimal. In fact, your beam becomes over reinforced when the applied moment exceeds the limiting moment, and in that case you have to redesign the section. So different things can be done. One option can be changing the cross-sectional dimensions of the member, or increasing the concrete strength, or designing the member as a doubly reinforced beam. So we have three options: either to change the cross-sectional size, or increase the material grade of your concrete, or you can put some reinforcement bar in the compressive zone and then design the beam as a doubly reinforced beam. So this brings us to the end of the analysis of singly reinforced section. In our next chapter, we will begin with the design of singly reinforced rectangular sections, but before that, we will have 2 classes relating to tutorial for this analysis portion. So we will meet again in our next tutorial class. Till then, stay safe and thank you.